thank the organizer committee for letting me the presentation. This presentation title is Laser Assisted Vacuum Electron Acceleration. So basically my work is in laser plasma interactions or laser vacuum interaction. So these are the outlines that first of all, I'll briefly describe what is this electron acceleration due to laser. Then I will describe the laser plasma interaction, some application part, some results and conclusion. So first of all, we can see that laser plasma interactions, what is it? So whenever we have a very intense laser beam for about 10 raised to power 19 watt per centimeter square is allowed to pass through the plasma, what will happen? It will interact with it and various nonlinear phenomena will occur. For example, self-focusing is there and some other phenomena are there. For example, we can have the secondary beam of X-rays, gamma rays, some nuclear radiations will be produced, for example, these positron, neutrons, and accelerated electrons. So this is my current field of interest, that is relativistic electrons, which are produced by the laser plasma interactions. So let us understand that what is accelerator actually. So this is particularly a device which is used to produce a beam of charged particles, and we can accelerate them with very high velocity, or we can say that with some nearly constant velocity or energy. And they are followed by the parallel trajectories. Small beam cross section can be observed. And we can have some various daily life applications. For example, we can see these applications of particle accelerator in normal television, computer monitor, microwave oven, oscilloscopes. Industrial uses are there. For example, it is used in food sterilization, electron microscopes, radiation treatment of materials, nuclear waste treatment. So many applications are there in medical, for example, cancer therapy, radiology, instrument sterilization and isotope production, and in the research tool for the scientific fields in high energy physics experiments, light sources for the chemistry, biology, and optics. And these are some medical applications for these particular electron accelerators, because we can have the GeV energy also produced from these electrons, and we can use these for we can say treating the cancer treatment, cancer tumors. And also in today we can see that it is widely used in the proton or ion accelerators instead of hadron therapies. Although we have some technical challenges also, we are working on it, and in the imaging also we are using it in the isotope production. And what are the basic drawbacks if we talk about the historical timeline? We are talking about the conventional accelerators, and they were radio frequency accelerators. So we know that the acceleration gradient is very small at that time, that is limited to approximately 100 MeV per meter only. The reason is that the walls of the accelerating structure, it can break. So it is a breakdown limit here. And obviously for energy more than 10 GeVs, the length of accelerators we have to increase only, that is in kilometers, which is very big and very expensive also. For example, here in SLAC, Stanford Linear Accelerator Center, we have very large accelerator facilities. These are the we can say machines which are producing 20 to 50 GeV electrons, and the length is 2.5 kilometers approximately. Similarly, in Large Hadron Collider at CERN, it is again so wide, that is 27 kilometer circumference is observed. And in the International Linear Collider also, we have approximately length in 31 kilometer if you want to produce 500 GeV electrons. So but I will talk about the solution also. First of all, let us understand that how we can use laser for accelerating the electrons. We have this condition to be fulfilled, that the strongest interaction, in fact, of the electrons with the wave occurs when the velocity of the electron is comparatively equal to the phase velocity of the wave. K dot VV is the velocity, and this omega. So in that way, what will happen? The resonant, we can say acceleration will be there. The resonance will take place if this condition is fulfilled. And in that case, what will happen? The Doppler shifted frequency of the wave will be equal to the electron frequency, that, and then in that case it will be accelerating. And what will happen if the laser is passing through the plasma? It will exert a longitudinal force on the electron, and the phase velocity will be equal to the velocity of the accelerating electron, so that the wave field appears quasi-static to the electron. And what will happen? The efficient energy transfer to the electron from the laser could take place. And what is the main advantage of using this fourth state of matter, plasma? So we know that the plasma is having very, very high acceleration gradient. This is, we can say that the maximum accelerating field gradient, which is limited by the plasma wave breaking, is approximately, the condition is there, the density of this plasma could be 10 raised to power 18 per cubic centimeter, and this E could be equal to 100 GeV per meter. So it is 1,000 times larger than the conventional radio frequency accelerator. So this is the reason that by using this plasma as a medium, we can produce very high acceleration gradient, and it is used in compact tabletop accelerators. So this is the phenomena of excitation of electron plasma waves, how the plasma wave will be produced and how it will excite the electron to such tremendous energies. So we have various phenomena. If we are using laser directly, then we can have some phenomena like plasma beat wave acceleration, self-modulated laser wake field acceleration, and simply laser wake field acceleration. Or if we are injecting the particle beam directly, it is a plasma wake field acceleration only. And as we can see that the plasma, it is having very high acceleration gradient. The reason is that because in conventional accelerators, we have the peak power limited, very limited because of the breakdown limit. In that case of plasma, it is already in that state, breakdown state. So there is no limit of such breakdown. And conventional accelerators have a very limited gradient, that is 50 to 100 MeV per meter only. But in the case of plasma as a medium, we can have 10 to 200 GeV per meter energy also. So these are some advantages of laser assisted accelerators, electron accelerators, due to the plasma as a medium. So it can have very high amplitude electric field also, and which is up to, we can say, acceleration gradient up to 200 GeV per meter than the conventional accelerators. But some major challenges are also there, like we have to take care of the phase matching condition of the electron beam with the laser. If it is fulfilled, then we can have the resonant acceleration of electrons. Also, somehow what happened, the energy spread is observed. So the production of monoenergetic beam, electron beam, is also a challenge here. And how the electron could be injected, what is the optimum phase of the electron, this is also very important parameter. And the large spread of energy band of the accelerated electron due to the trapping of electron is also a challenge to be overcome. So these are some of the solutions we have done so far in our research papers. We can maintain the acceleration distance also. One method is to use a plasma channel such as the capillary discharge waveguides. We can reduce the energy spread also. We can reduce the diffraction also. See, one way is to increase the spot size of the laser beam, because it can reduce the diffraction. But the trouble is also there that if you increase the spot size of the laser, what will happen? We have to quadruple the laser power also. So just to maintain the same intensity, it is really tough. And if you increase the spot size enough to achieve 1 GeV beam, electron beam, it would require very high power laser, a 10 raised to power 20 watt per centimeter square, approximately petawatt lasers, which is really expensive and cumbersome. So alternate way, we can say that we can increase the acceleration length to provide a guiding channel for the drive laser pulse, which can create the plasma wake field. So by the plasma wake field method, we can reduce this kind of diffraction. So this is the publication which is in the year 2019. In that case, we have observed the influence of external magnetic fields. Also, we have taken circularly polarized laser beam especially, and the field distribution of that circularly beam is given as this equation. We can see the direction of propagation is Z. These are some components: cos omega t minus kz for the x, and sine omega t minus kz for the y. And here R naught is a spot size, initial spot size of the laser. Tau is the duration of the laser. Vg is a group velocity, and R is an instantaneous spot size. Here K is a wave vector which is given by omega by c into under root of 1 minus this omega p. Omega p is here plasma frequency divided by normal omega, that is a laser frequency. Here group velocity of laser is also given, and this is the plasma frequency equation, where N naught is a plasma density, E is a charge of electron, and M is a mass of electron respectively. So here electric field of this laser could be estimated from this equation, that is dA by dt, negative sign, and this is your magnetic field which is associated with this laser electric field, which can be calculated from this equation. And the external magnetic field which we can apply is azimuthal magnetic field and axial magnetic field. So we have taken the axial magnetic field along the direction Z, and these are some results which we have observed, that this is your maximum electron energy gain. What is the maximum energy gain in GeV could be observed with applying the magnetic field. This is the magnetic field along the horizontal axis, and this is the normalized value of magnetic field in few kilogauss. So we can see the peaks here, and these peaks depicts the optimum value of the magnetic field for effective acceleration for different intensities of laser. These are some different initial intensities of laser normalized values. It is approximately 1.38 into 10 raised to power 18 watt per centimeter square. So we can see that as a laser intensity is changed, the value of magnetic field which is required is also changing for the resonance. Obviously, we can observe good energies with lesser values also, but these are the optimum values of the magnetic field required. And we can also see that at what particular intensity and the magnetic field combination we can achieve how much maximum energy gain. So we have taken the values like other parameters like initial momentum is normalized value is taken 1. The wave vector value is taken 0.98. Z naught is the initial position of that electron, and the pulse duration is also in femtoseconds. It is a normalized value 300. So these are some diagrams, some graphs which we have seen, which we have observed for various initial spot size. So we can also see that as a spot size is increasing, what will happen? The spreading will be more, and in fact, the energy will be less. So here for 13 micrometer laser spot size, we can observe much higher energies in GeVs, approximately 2.2 GeV. And this is the propagation axis. It is the normalized values only. Similarly, here we have observed that for what particular pair of the intensity, laser intensity and spot size, we can produce how much energy. For example, here I have observed that for the initial intensity normalized value 10, that is approximately 5.1 into 10 raised to power 18 watt per centimeter square. The spot size is in micrometers. We can observe approximately 2.4 GeV electron energy gain. So these are the optimum values we can see here with the calibration graph. And in this case, we have seen the impact of the pulse duration of this laser. For example, it is varied from 53 femtosecond to 532 femtosecond. And we can see that as the pulse duration is increased, the interaction of the laser and electron will be more. And in that case, what will happen? The energy gain will be increasing. And in this case, we have observed the acceleration gradient in blue peak, this one, and this is our energy gain in gamma. Gamma is your energy gain of electron, and this is the acceleration gradient. So we can also see that how it is varying for the intensity A naught equal to 10, the optimum magnetic field value for resonance 0.09, which is few kilo Gauss only, and this is the effective acceleration gradient. It is approximately 52 GeV per meter. It is observed with the maximum energy gain of about 2.2 GeV. And this is the observations for the various intensities with the axial magnetic field only, and with the combined effect of the axial and the azimuthal magnetic field. So this circularly polarized laser is giving more acceleration of electron with the combined effect of these two magnetic fields as compared to the single one. And these are the respective acceleration gradients, the peak value of the gradient, which could be achieved from these particular values of the laser initial intensity. We can see here for different initial intensities of lasers, we could have different values of this acceleration gradient. It is a function of this propagation distance z dash normalized value. And here we have taken the tightly focused chirped laser pulse. So we can see that as the intensity is increasing, the acceleration gradient is also increased, provided we have optimized the resonance condition. So we can conclude that the result of this work is showing really showing a significant improvement in the electron energy gain. By observing these results, we can minimize the diffraction losses as compared to the other previous work reported by in this field by the previous investigators. So this work is quite useful for the reduction of the diffraction losses. So that is all for this talk. Thank you everyone for your attention.
Thank you so much, Dr. Joyti. So floor is open for the questions. If anyone having the questions. I can't see any question. Thank you, Dr.
Okay.
Thanks for your presentation.
A question from here.
Yeah, there is one question. Yes.
Experimentally, like what's the achievable interaction length that you have seen?
Actually, this work is not experimental work. It is a theoretical work. We are solving the equations, we are normalizing the equations, and we are comparing with the experimental data.
Yeah, that's what I mean. I mean, well, what's the current state of art like in this experiment?
Yes, so we are comparing the results, and we can achieve GeV electron energy gain with the petawatt lasers also, terawatt lasers also. So these all parameters which I have taken here is feasible. In the paper, in one of my paper in laser physics, I have given the facilities also where this things could be done, and the higher version could be done like this.
Yeah, thank you.
Any further question from the floor?